Industrial power plants operate under extreme thermal conditions. Generating steam for commercial turbines means pushing boilers to outputs of 140 bar and 540 degrees Celsius. Feeding these high-capacity boilers requires a massive, continuous fuel supply. Agrobiomass offers that industrial scale, providing millions of tons of harvestable residue every year. This fuel category includes a variety of organic crop residues left over after primary harvests, such as paddy straw, wheat straw, and mustard residues. Utilizing these residues directly from the field introduces physical constraints. A single delivery can span a massive moisture spectrum, with the water weight of the fuel ranging from 10% to 60%. But the true engineering bottleneck is chemical. Agrobiomass possesses high concentrations of alkali metals and silica, which drastically lowers the temperature at which its ash melts. This chart plots the low ash melting point of high alkali biomass against the standard temperatures inside an industrial furnace. In the highlighted overlap zone, the organic matter burns, but the remaining ash melts into a corrosive, sticky slag. Managing this specific alkali slagging is the primary engineering barrier in biomass energy. If a power plant cannot stop the ash from fusing into solid rock inside the boiler, agricultural residues cannot be scaled for commercial power generation. Traditional combustion systems typically rely on air-cooled traveling grates. These function like heavy-duty conveyor belts, dragging fuel through the furnace using a complex series of internal mechanical linkages and rollers. Because these grates rely on incoming primary combustion air to cool their steel components, their metal temperature fluctuates. If the airflow is adjusted to manage the fire, the cooling effect drops, creating sudden thermal spikes across the grate. At 540 degrees Celsius, those thermal spikes trigger alkali sintering. The molten ash fuses directly onto the moving links and rollers operating inside the hot zone, leading to mechanical jamming and system failure. Burmeister and Wayne Energy engineered a solution to this failure loop, the water-cooled vibrating grate, or WCVG. The structure abandons internal moving mechanical links. Instead, it utilizes a rigid membrane wall, suspended entirely on external elastic elements. Replacing a kinetic transport belt with a solid-state combustion platform stabilizes the thermodynamic environment, removing the internal machinery that alkali slag typically destroys. To process high alkali fuels continuously, the system must lock the temperature of the grate surface well below the ash melting point, regardless of the fire burning directly on top of it. Look at the physical assembly of the membrane wall panel. It is constructed from parallel steel water tubes welded together with continuous steel fins, creating a sealed, flat plane. This surface operates as an integrated piece of the boiler's primary natural circulation evaporator circuit. The same high-pressure feedwater generating steam in the walls above is routed directly through the floor of the grate. It is not a separate low-temperature cooling loop. The grate is actively pumped with the boiler's main 140 bar water supply. This continuous flow locks the grate's surface metal temperature between 250 and 320 degrees Celsius. It cannot spike, and it cannot overheat. Because 320 degrees is far colder than the alkali ash softening point, the ash cannot melt upon contact. As the hot particles hit the cold steel, they harden and bounce off as solid, manageable grit. Embedding the grate directly into the boiler's primary thermodynamic cycle eliminates the physical mechanism of structural slagging. The ash cannot find a surface hot enough to stick to. A 150 megawatt fire requires a massive volume of oxygen. The challenge is supplying that air to the fuel bed without driving the local temperature past the 800-degree ash melting point. The solution relies on precise fluid dynamics. Primary combustion air nozzles are drilled directly into the steel membrane wall fins nestled between the cooling tubes. Through these fin orifices, the system supplies a restricted volume of primary air, accounting for only 30% of the total oxygen required for combustion. This deliberate restriction starves the fuel bed of oxygen. By choking the combustion at the base layer, the system keeps the bed temperature below the 900-degree threshold where alkali sintering begins. The remaining 70% of the air is injected as ignition and overfire air at multiple higher elevations throughout the furnace. Once the volatile gases release from the choking bed and rise into this oxygen-rich upper zone, they ignite, achieving complete carbon burnout in the open space of the furnace. This staging prevents the formation of nitrogen oxides. By depriving the high-temperature bed of the oxygen required to bond with fuel nitrogen, and by lowering peak flame temperatures in the secondary zone, the system suppresses both fuel and thermal NOx. This 30-70 split creates two isolated environments, a low-temperature zone on the grate to keep solid ash from melting, and a high-temperature zone above for total gaseous burnout. Welded into a rigid plane, the grate lacks internal chains to move the fuel forward. The raw biomass still needs a transport mechanism to progress through the furnace. The entire water-cooled membrane structure is tilted on an incline. Crucially, the assembly is suspended on heavy-duty elastic brackets located completely outside the combustion chamber. Connected to the exterior of the grate are eccentric vibration drives. These motors deliver precise, intermittent bursts of kinetic vibration through the rigid panel. Each vibration burst slightly fluidizes the biomass bed. The kinetic energy bounces the fuel, stepping the mass down the incline while maintaining an even bed thickness for air penetration. As the fuel hops down the top half of the incline, radiant heat dries the material in the heating zone, followed by the devolatilization zone, where volatile gases are released. On the lower half, the remaining carbon undergoes burnout. Finally, the residual ash enters the cooling zone, chilled by incoming undergrate air before discharging into a hopper. Isolating the drive motors and support elements on the cool exterior means the mechanical components that generate the movement never face thermal fatigue. The vibration source is separated from the fire. At an industrial scale, a commercial plant must ingest hundreds of thousands of tons of this fuel year-round without pausing for internal repairs. This chart compares boiler longevity. Left, an air-cooled grate endures load-dependent temperature spikes that fatigue metal. Right, the WCVG keeps thermal loads completely flat. Protected by internal water pressure and lacking friction chains, membrane lifespans exceed 10 to 15 years with minimal maintenance. Beyond durability, there is a hidden efficiency gain. Powering an intermittent vibration motor draws drastically less electricity than constantly driving heavy mechanical chains and continuous cooling fans. Moving from a structure that requires annual grate bar replacements to a membrane wall with a 15-year lifespan lowers the fixed operating costs and increases the plant's total annual uptime. These thermodynamic principles power high-efficiency agricultural waste facilities globally, including the Sleaford biomass plant. The flat grate geometry also allows operators to adapt to seasonal fuel supplies, transitioning between wet straw and forestry residues without needing to alter the internal mechanics. By thermodynamically locking the grate temperature and isolating the transport mechanics, the BWE WCVG serves as the primary technical standard for high-alkali biomass power generation.